Good evening. Today we are discussing surface area. We are discussing surface area of solid of revolution. Solid of a revolution. First of all, you must know how we can find a surface area by revolving one area about x-axis or y-axis. First of all, consider an arc y is equal to f of x. Consider an arc y is equal to f of x. X is equal to a, one ordinate. X is equal to b, another ordinate, x-axis. When this is the area bounded by an arc of a curve between two ordinates, x is equal to a, x is equal to b, and the x-axis. When this area is rotated about x-axis, we can imagine one solid. By imagining that solid, we can find a volume of that solid of revolution. We can obtain the volume of the solid of revolution. How? Now that we can find a volume, we can also find surface area of the solid of revolution. Volume we have obtained last class, and today we are discussing surface area of the solid of revolution. Now, when this area is rotated about x-axis, a solid is generated. Surface area of the solid generated is given by the formula 2 pi integral a to b. A is this, b is this, y times square root of 1 plus dy by dx whole square dx. This is the surface area of the solid of a revolution. If you rotate this area about x-axis, we use this formula. If we use x coordinates, we use this formula. We find a dy by dx for the given curve. Substitute here, square it, add 1, take square root, multiply by y. Again, y can be taken from the equation of the curve. Integrate the whole function with respect to x, multiply by 2a. That gives surface area of the solid of a revolution. Instead, you consider the curve x is equal to f of y. X is expressed in terms of y. You take horizontal lines y is equal to c and y is equal to d. This is our y-axis. This area is rotated about y-axis. Instead of rotating about x-axis, we are rotating the area about y-axis. This area is rotated about y-axis. Again, some solid is generated. For that solid, we can find volume and surface area. Last class we obtained a volume. Now we are finding surface area of the solid of revolution by rotating an area about y-axis. That is given by the formula 2 pi integral c to d x times root of 1 plus dx by dy whole square dy. We integrate this with respect to y. We find a dx by dy from the equation of an arc, equation of the curve. Now, up to school level, we find area, volume, surface area, all these things. We take it for granted. Only in high level, that is in higher secondary level, plus 2 level, we derive the formula for surface area of a sphere, surface area of a cone, everything by this methodology. Let us find the surface area obtained. Problem number 1. Find the surface area of a sphere. Of radius a. Now our job is to find the surface area of a sphere of radius a. Already we have used this formula in school level, but here we are deriving the formula how to find the surface area of a sphere of radius a. First of all, you consider a circle of radius a. You consider a circle of radius A, center at the origin. Center at the origin. We all know x square plus y square is equal to a square is the equation of a circle. Center at the origin. Center at the origin. Radius A units. So automatically this is A0 because the circle is symmetrical about x-axis. It is also symmetrical about y-axis. Automatically we can say this is 0A, this is 0A, this is minus A0, or minus A0, this is 0 minus A. These are the 4 points lying on a circle. Lying on a circle. Now to generate a sphere, we imagine this area. You imagine this area and rotate this area, that is area above the x-axis. We rotate this area about x-axis. By rotating this area about x-axis, we are generating a sphere. We have to imagine we are generating a sphere. So surface area of that sphere is given by the formula. Surface area of the sphere is given by the formula 2 pi. I mentioned here minus A to plus A. Earlier I mentioned A to B. Here A is minus A, B is A. Minus A to plus A. Minus A to plus A. Y times square root of, since we are rotating about x-axis, we use the first formula 1 plus dy by dx whole square. 1 plus dy by dx whole square. We integrate with respect to x. We integrate with respect to x. So dy by dx is obtained for this curve. Dy by dx is obtained for because this is our arc. This is our arc. So you find a dy by dx for this curve. Limits are minus a to plus a. Y times root of 1 plus dy by dx whole square dx. 2 pi times gives the surface area of sphere of radius a. Now let us find dy by dx and we will use this formula once again. Now consider x square plus y square is equal to a square. We are solving the problem right from the scratch. We are finding dy by dx in a systematic way. This is an implicit function. Y is not expressed in terms of x. X and y are connected. Therefore 2x plus 2y dy by dx. 2y dy by dx is equal to 0. Differentiating y square, 2y. Again y is a function of x. Therefore function of function rule applying that, you get dy by dx. So cancelling 2, you get y times dy by dx. Y times dy by dx is minus x. Therefore dy by dx for this curve is nothing but minus x by y. Is nothing but minus x by y. So we have obtained a dy by dx for the curve. We want the simplification of 1 plus dy by dx whole square because it is involved in the formula. So therefore let us find root of 1 plus dy by dx whole square, that is 1 plus x square by y square. Squaring a negative quantity, we get a positive quantity x square by y square. Taking LCM, you get a square root of x square plus y square. X square plus y square by root of y square y. X square plus y square is a square. Therefore root of a square is a by y. So this is complete simplification of square root of 1 plus dy by dx whole square. So find dy by dx, substitute here, take LCM, x square plus y square is replaced by a square at any stage, and x square plus y square is a square, root of a square is a, and root of y square is y. So they will get a by y. I am substituting everything in the given formula. Therefore surface area is given by 2 pi integral minus a to plus a y times square root of 1 plus dy by dx whole square. Dy by dx whole square dx. Just now we have simplified a dy by dx whole square, 1 plus that, all these things. Therefore y times a by y. Y times a by y. So again y gets cancelled. Again y gets cancelled. We are getting a mere constant. Mere constant means automatically it is an even function. It's an even function. By applying property of a definite integral, minus a to plus a fx dx is 2 times 0 to a. Therefore this becomes 4 pi times 0 to a dx. Applying the property, this 2 times 0 to a, already 2 is there, we get 4 pi times 0 to a dx. So therefore ultimately 4 pi a is a constant taken out. Integrating 1 we get x. Applying upper limit and lower limit we get automatically 4 pi a times
a minus 0. Upper limit is a, lower limit is 0. So upper limit minus lower limit, according to that definition, we get 4 pi a square. So surface area of a sphere, is obtained as 4 pi a square units. Is obtained as 4 pi a square units. So we have taken it for granted up to 10th standard, up to 11th standard. Only in 12th standard we derive the formula for surface area of sphere, surface area for cone, surface area for all solids we can obtain by the methodology using this integration. Okay. Now this is a very simple problem. Let us take one complicated problem. Let us consider a second problem under surface area. The problem is obtain the surface area of asteroid. An asteroid. It's a beautiful curve. Asteroid is a beautiful curve. You all know how to trace the asteroid. This asteroid, by understanding this asteroid, we understand many concepts. It is an IIT question. By answering this question, you get a lot of points. We get almost all properties here. At the same time, we are using reduction formula. We are tracing the curve in a systematic way. So this problem contains so many points. It will be very useful for facing any competitive examination. Asteroid is nothing but x power 2 by 3 plus y power 2 by 3 is equal to a power 2 by 3 is our asteroid. We know power of x and power of y are equal. Therefore, the curve is symmetrical about x-axis and y-axis. At the same time, it is even. You can ask one question, why it is even? Power 2 by 3 is there, how can it be even? We write this in the form x power 1 by 3 whole square, y power 1 by 3 whole square is equal to a power 2 by 3. Now power is even, 2, 2. So therefore, power of x and power of y are equal and even. Therefore, the curve is symmetrical about x-axis and y-axis. At the same time, it is not a circle. First of all, let us find where it cuts x-axis. In the equation of the curve, the tracing is very important. Tracing part is very important for a competitive examination. Put y is equal to 0 to find where it cuts x-axis, where it crosses the x-axis. X power 2 by 3 is a power 2 by 3. X square is a square. Automatically x is equal to plus or minus a. So therefore the curve crosses x-axis at a0 and minus a0. Crosses x-axis at a0 and minus a0. X is a, y is 0. X is minus a, y 0. Similarly, by giving x0, you get y. Y is plus or minus a. So the curve also crosses x-axis at these 2 points, 0a and 0 minus a. 0a and 0 minus a. So hence we get a curve. Which is symmetrical about x-axis. It is also symmetrical about y-axis. Therefore, you get a symmetrical curve exactly like this. You get a beautiful symmetrical curve. Because if you get an arc like this, you get an arc like this because it is symmetrical about x-axis. If you get an arc like this, you get an arc like this because it is symmetrical about y-axis. If you get an arc like this, you will be getting an arc like this. Therefore, it is symmetrical about y-axis. So therefore, the entire asteroid, this is called asteroid. This curve is called asteroid. This asteroid is symmetrical about x-axis and y-axis. And just now we have seen it cuts x-axis at a0 and minus a0. It cuts y-axis at 0a and 0 minus a. Now once you know the tracing of the curve, we are rotating this asteroid. We can rotate area above the x-axis or area below the x-axis. Ultimately, by rotating, you get the same solid. So once you know that, we are rotating this area above the x-axis to find the volume of the solid generated by rotating an asteroid about x-axis. That volume as well as surface area. So volume we have seen. Surface area is given by 2 pi integral minus a to plus a
y times root of 1 plus dy by dx whole square. I am writing y dash square dx. So this is the formula to find surface area. We need y, we need y dash, and equation of a curve is given. Once the equation of curve is given, for this particular problem, we are converting everything in terms of parametric equations. The parameter is theta, that will be used for tracing the curve. So therefore, I am converting everything in terms of parametric equation. That conversion is very important. Let us analyze that one by one. First of all, I am taking the parametric equations of the curve. X is equal to a cos cube theta and y is equal to a sin cube theta. X is equal to a cos cube theta and y is equal to a sin cube theta. These are the parametric equations of this curve. Now, what do you mean by parametric equations? The parametric equations, by varying theta, you get various x and y. Automatically, we can get almost all points. We can get almost all points on the curve. For a tracing. And first of all, we are finding these parametric equations. After finding these parametric equations, we are finding dy by dx. Dx by d theta is nothing but 3a cos square theta minus sin theta. Dy by d theta is nothing but 3a sin square theta cos theta. So we are finding dx by d theta and dy by d theta. Thereby we are finding dy by dx for the curve. In terms of parameter, dividing this by this, you get a 3a sin square theta cos theta divided by minus 3a cos square theta sin theta. Automatically 3a gets cancelled, 1 sin theta gets cancelled, 1 cos theta gets cancelled, giving only minus tan theta. This is our dy by dx. Now, once you convert the equation in terms of parametric equation, this x and y satisfies the given equation. That's why they are called the parametric equations. And you must know the limit for theta also. We know limit for x. We want limit for theta. Now, from the equation of a curve, see, from the curve which I have drawn, a symmetrical curve which I have drawn, automatically here theta is equal to 0. Here theta is equal to pi by 2. Here theta is equal to pi. Here theta is equal to 3 pi by 2. Again, by varying theta, you get various points on the curve. Theta 0 to pi by 2, you get these points. Pi by 2 to pi, you get these points. Pi to 3 pi by 2, you get these points. 3 pi by 2 to 2 pi, you get these points. So therefore, surface area of the solid of revolution is nothing but 2 pi integral. Now minus a, when x is minus a, theta is pi. When x is minus a, theta is pi. When x is plus a, theta is 0. Corresponding theta we are taking because we are using parametric equations. Y is nothing but a sin cube theta. Root of 1 plus dy by dx whole square. Dy by dx whole square, we have seen it is tan square theta. And dx is nothing but x is equal to a cos cube theta. Therefore, dx is nothing but 3a cos square theta minus sin theta d theta. This is nothing but a differential. So therefore, you get minus 3a cos square theta sin theta d theta. This is our complete integral. You can ask one question. Why, sir, we are converting everything in terms of theta? If you retain in terms of x, integration will be complicated. Now, fortunately, we are getting a very simple integral. Let us see how. First of all, minus pi to plus 0, minus pi to 0, minus sign, we can make it as plus. That integral, we can make it as plus 0 to pi because of this minus sign. According to a property, minus a to b fx dx is the same as b to a fx dx. I am removing negative sign by making positive sign here. 2 pi is here, a is here, 3a is here, 3a square, 2 pi, 6 pi a square. We are getting 6 pi a square. Later on you can take it out, it's a constant. Sin cube theta Sin theta, sin power 4 theta, sin power 4 theta. 1 plus tan square theta is secant square theta, secant theta, 1 secant theta gets cancelled with this cos square theta, giving only cos theta, d theta. I repeat again. 1 plus tan square theta is secant square theta. Root of secant square theta is secant theta. Secant theta, cos theta. 1 cos theta gets cancelled because secant theta is the reciprocal of cos theta. 1 cos theta gets cancelled, giving exactly 1 cos theta here, and sin theta, sin cube theta, sin power 4 theta. Now, our integration is very simple. At the same time, we can also apply reduction formula. Because we can convert this 0 to pi as 2 times 0 to pi by 2. Once you are able to convert 0 to pi as 2 times 0 to pi by 2, the reduction formula can be applied. Now, what is the criteria for that? We are having a criteria for that. That criteria is, I will write down the criteria here. 0 to 2a fx dx. 0 to 2a fx dx is 2 times 0 to a fx dx. 2 times 0 to a fx dx, provided f of 2a minus x is equal to f of x. F of 2a minus x is equal to f of x. Now, what happens to f of 2a minus x here? We can apply all these things. So, if you find that difficult, directly we can make use of substitution. And integrate. Okay. Now, before that, what I am doing is, I am converting this as 0 to pi by 2 because of symmetry. You can make use of this argument, this property, or symmetrical property. You can also apply. So, therefore, whether you rotate this area, or you rotate this area and multiply by 2, both remains the same because of symmetry, because it is symmetrical about x-axis and y-axis. So we are writing this 12 pi a square 0 to pi by 2. So 12 pi a square 0 to pi by 2 sin power 4 theta cos theta d theta. Now directly we are applying a reduction formula. Reduction formula means if you have 4, start with the 3, going on diminishing by 2 until you reach 1 or 2. Here we are reaching 1, stop. If you have 1, start with 1, end with 1. 4 plus 1, 5, 5, 3, 1. No pi by 2 because one number is odd. So simplifying this, you get automatically 12 pi a square by 5. We are getting 12 pi a square by 5. So therefore, we can simply say the volume and surface area. Volume already we have found. Now we are finding only surface area. Surface area of the solid generated by rotating an asteroid. About x-axis is nothing but 12 pi a square by 5. 12 pi a square by 5. It's a very interesting, important problem because it involves so many concepts. One reduction formula involving sin and cos, another one property 0 to 2 pi or 0 to pi 2 times 0 to pi by 2. Another thing, symmetry about x-axis, symmetry about y-axis, all these things. So many concepts are involved in this problem. That's why this kind of problems are very important for facing so many competitive examination. In particular IIT, MSET, this particular problem is very important, and IIT, MSET, VIT, Amrutamaya, for all these things, for all competitive examinations of this kind, this particular problem is very important. Okay, one more problem we'll take, and with that we go to the next chapter, namely reduction formula. Now we are taking cycloid. Now. Find the volume already we have found. Find the surface area by rotating one arc of the cycloid about x-axis. Let us recollect what is cycloid. You take a circle. You take any particular point. You observe that point and trace a curve where the point moves. Suppose initially the point P is here. As the circle rotates, the point P will describe an arc. As the circle rotates, you take a particular point, that particular point will describe an arc. So again the point, the circle will be here, the point P will be here. So therefore again it revolves, we get an arc like this, it's called a cycloid. So a cycloid is nothing but path traced by a point on a circle, path traced by a point on a circle, As the circle revolves, automatically point P will describe an arc, and that arc is called a cycloid. Now, what's the equation of cycloid? Next question. X is equal to A into theta minus sin theta, and Y is equal to A into 1 minus cos theta are the parametric equations of a cycloid. Directly I am giving a parametric equation. Why so? Because actual equation of cycloid in Cartesian form, it is not obtained here. Of course, there is great difficulty eliminating theta from these two equations. We can find a relation between x and y. It is tedious. We will be getting a tedious curve, and to avoid that, we are taking parametric equations directly for a cycloid. Okay, for a cycloid, we can trace a cycloid. By taking some points. When theta is 0, 0, sin 0, 0, x is 0, cos 0 is 1, 1 minus 1, 0, we are getting 0, 0, 1 point. When theta is pi by 2, cos sin 90 is 1, you get a times pi by 2 minus 1. Cos 90 is 0, you get a. When theta is pi, sin pi is 0, you get a pi here. Cos pi is minus 1, you get 2a here. When theta is 2 pi, sin 2 pi 0, 2a pi here, you get 2a pi. Cos 2 pi, even multiple 1 minus 1, 0. So therefore, starting with y0, we are getting again y0 when theta varies from 0 to 2 pi. That shows we are getting a tracing of curve. We are getting a beautiful curve. Like this. Let us trace the curve. Here theta is equal to 0. Here theta is equal to 2 pi. Theta is equal to 0. Here theta is equal to 2 pi. From this to this, y becomes 0. Y means height is 0. Therefore, it is on the x-axis. So therefore, this cycloid, and take this area and rotate about x-axis, a solid is generated. The surface area of the solid generated is given by the formula 2 pi integral theta varies from 0 to 2 pi. So I am taking directly theta. Theta varies from 0 to 2 pi. Y into root of 1 plus dy by dx whole square dx. Only thing is, you must convert everything in terms of theta because we have taken limits for theta. So you must convert everything in terms of theta. Let us do it patiently. Okay. Now, first of all, x is equal to a into theta minus sin theta. Let us find a dx by d theta. That is a into 1 minus cos theta. You take y is equal to a into 1 minus cos theta. dy by d theta is nothing but a sin theta. Therefore, dy by dx for the curve is a sin theta by a into 1 minus cos theta. So automatically 2 sin theta by 2 cos theta by 2 by 2 sin square theta by 2, that gives ultimately cot theta by 2. So therefore, first of all, find dy by dx in a systematic way. By finding dy by dx, we get cot theta by 2. Once you know dy by dx, we are directly finding the surface area like this. So surface area is 2 pi integral theta varies from 0 to 2 pi. Y is a into 1 minus cos theta. Square root of 1 plus dy by dx whole square. Dy by dx is cot theta by 2. Therefore, you get cot square theta by 2. Dx, x is a into theta minus sin theta. Therefore, automatically
taking differential a into 1 minus cos theta d theta. So again you get a into 1 minus cos theta d theta. That's all. Everything is over. We have to integrate in a systematic way. These two can be grouped. These two can be grouped. Now, so 2 pi 0 to 2 pi a square 1 minus cos theta whole square. Because 1 minus cos theta, two factors, 1 minus cos. You know cosecant square theta minus cot square theta is 1. Therefore, cosecant square theta, we all know, cosecant square theta minus cot square theta is 1. Therefore, 1 plus cot square theta is cosecant square theta. Therefore, 1 plus cot square theta is cosecant square theta. Since we are having theta by 2 here, we are having theta by 2 here. We write cosecant square theta by 2. We write cosecant square theta by 2, taking square root, you get cosecant theta by 2 d theta. Over. Integration is over. Now 2 pi a square 0 to 2 pi 1 plus 1 minus cos theta is 2 sin square theta by 2. You get 4 sin power 4 theta by 2. You get cosecant theta by 2 d theta. So 1 minus cos theta is 2 sin square. 2 square 4 sin square theta by 2 sin power 4 theta by 2 because power 2 is there. 1 cosecant theta by 2 gets cancelled with 1 sin theta by 2. One is the reciprocal of the other. We are having 4 sin cube theta by 2. We are having a major point. You can ask one question. Can you apply reduction formula here? No. Because limits are 0 to 2 pi. We cannot apply. At the same time, argument is theta by 2. We cannot apply. So you must know all criteria for applying reduction formula. So what we do is, first of all, I am converting theta by 2 as t. I am converting theta by 2 as t. So I want to retain this step, that's why I am erasing like this. Otherwise totally we can erase 2 pi a square. 2 pi a square. 4 is there, you get 8 pi a square. 8 pi a square. Integral 0 to 2 pi sin power 3 theta by 2 d theta. I am replacing theta by 2 as t. I told you cannot have argument as 3 theta, theta by 2, theta by 3, all these things. We cannot apply reduction formula. For that I am replacing this theta by 2 as t. Therefore theta becomes 2t. Therefore d theta becomes 2 dt. Taking the differentials. Now you can change the limits. Another point is, whenever substitution is given, necessarily we have to change the limits. When theta is 0, automatically t is 0. When theta is 2 pi, we get t becomes pi. So therefore, I am applying. I am making use of the substitution. I am reducing to a simplest form so that we can easily apply finally reduction formula and get the answer. Okay. So with this, we are having 8 pi a square 0 t is 0, theta is 0, t is 0. When theta is 2 pi, we get pi, we get 0 to pi sin cubed t, d theta is 2 dt, you get 16, you get 16 dt, 16 dt. Now, we can ask one question. Can you apply reduction formula? No, even now we cannot apply reduction formula. Even now we cannot apply. Why? The answer is, we are having 0 to pi. If you have 0 to pi, we cannot apply reduction formula. Reduction formula can be applied only when for sin power n theta. You can apply reduction formula only when if you have 0 to pi by 2. For that we are having sixth property. We are having sixth property. That property says 0 to 2a fx dx is written as 2 times 0 to a fx dx, provided f of 2a minus x is equal to f of x. So I am applying that property. 16 pi a square 2 times 0 to pi by 2 sin cubed t dt. Because sin pi minus t is sin t, that property can be applied jolly well. So therefore 32 32 pi a square. Apply reduction formula for sin cube t. You start with 2, end with 2. 3 means start with 3, end with 3. We get 64 pi a square by 3 square units. This is the surface area of a cycloid when it is rotated, when one arc of the cycloid is rotated about x-axis. Okay. So with this, we are completing definite integrals. Now we take definite integrals part 2, reduction formula under that. We take reduction formula under that. This reduction formula is a very important section under integration, because we are finding a relation between so many integrals. First of all, for an example, if we call this integral as In, this integral involving n, log x power n you have, we call this as In. Then automatically I2 will be integral log x power 2. If you have 2 here, we get 2 here. If you have 5 here, you get 5. I5 will be log x power 5. In minus 1, log x power n minus 1. In minus 2, log x power n minus 2. I1, log x power 1. Now, is it possible for us to find a relation between In and In minus 1? One question. Is it possible to find a relation between In and In minus 2? Sometimes it is possible for us to find a relation between In minus 1, In minus 2. Even if you have a definite integral or indefinite integral, we can find a relation between the successive integrals by changing the suffixes n minus 1, n minus 2 and so on. Now we are seeing some of the aspects of reduction formula. We can establish a relation between In minus 1 and In minus 2. This relation is called a reduction formula, and this reduction formula can be used to find the value of a definite integral a to be log x power n for all positive integer. That is very important. We are not using negative integer, we are not using a rational number, we are not using irrational numbers. This reduction formula can be applied only for n being a positive integer. Now see here. First of all, we are having a reduction formula for 0 to pi by 2 sin x power n. 0 to pi by 2 sin x power n. First of all, let us establish this. In is nothing but 0 to pi by 2 sin x power n. So the reduction formula is In is equal to n minus 1 by n In minus 2. N minus 1 by n In minus 2. What's the advantage of this? Once you know I10, we can express I10 in terms of I8. Once you know I8, we can express I8 in terms of I6. Once you know I6, we can express in terms of I4. Once you know I4, we can express in terms of I2. Once you know I2, we can stop with I0. 2, we are going on diminishing by 2. So In, this is established result, and by establishing this reduction formula, we can get the value of this sin x power n for all n. N can be 2013 also, even n can be 1 lakh, n can be any big number. We can apply this reduction formula and find its value easily. Now for that, I am giving complete reduction formula, complete value of this sin x power n. Sin x power n. When n is even, first of all, n is an even integer. It can be 10, 12, 18 like that. The reduction formula is start with n minus 1. We need not integrate. Start with n minus 1, going on diminishing by 2, until you reach 1. Start with n, going on diminishing by 2 until you reach 2. If n is even, we write pi by 2. If n is odd, no pi by 2. So the reduction formula is n minus 1, n minus 3, etc. You will be reaching 2 here first. Here n minus 2,
etc. You will be reaching 3 here, no pi by 2 if n is odd. If n is odd. So therefore, this is the reduction formula for sin x power n. This is the reduction formula for sin x power n when n is even, n is odd. Now I will give an example for this. So in the examination hall, if you have 0 to pi by 2 sin x power 10, very difficult to integrate. It will take more than 40 minutes. It will take more than 40 minutes to integrate this if you do it in a systematic way. Whereas by applying the reduction formula, you start with n minus 1, going on diminishing by 2, going on diminishing by 2 until you reach 1. Because we are having even number, it will be reaching 1. Start with 10, going on diminishing by 2, going on diminishing by 2 until you reach 2. Into pi by 2 because n is even. So simplifying this, you get the value of this definite integral. Similarly, 0 to pi by 2, if you have an odd number, say sin x power 7, sin x power 7. Start with n minus 1, going on diminishing by 2 until you reach 2 or 1. Here we are reaching 2. Stop with that. 7, 5, 3. If you want, you can write 1 or you can stop with this. So this is the value of this definite integral using reduction formula. That reduction formula I have been already. So this is the value of this definite integral. Now, we are having another question. Can you write reduction formula for cos x power n? Can you write reduction formula for cos x power n? When n is even, n is odd. One property says 0 to a, just now we have seen, or last class we have seen, 0 to a fx dx is same as 0 to a f of a minus x dx. F of a minus x dx. So if the definite integral, if the lower limit is 0, in the integrand x can be replaced by upper limit minus x. That's a property. Here the lower limit is 0, x can be replaced by pi by 2 minus x, you get sin x power n. So therefore, reduction formula for cos x power n is same as reduction formula for sin x power n. So 0 to pi by 2 cos x power n is same as 0 to pi by 2 sin x power n. Therefore, there is no change. Same reduction formula, right? N minus 1, n minus 3, etc. up to 1 by n minus 2, etc. up to 2 into pi by 2 when it is even. Otherwise, no pi by 2. So therefore, we can obtain the reduction formula for sin x power n, reduction formula for cos x power n. Now, for IIT level, for facing IIT competitive examination, we must derive reduction formula for tan x power n, which is very, very important. I think we can stop with this 0 to pi by 4. Here I am introducing limit 0 to pi by 4. You can get the reason for it. Tan x power n dx. Remember, reduction formula for sin x power n, reduction formula for cos x power n, they are different. Reduction formula for tan x power n is totally different because we integrate in a different way. By doing some jugglery. Let us see. You can enjoy that jugglery. First of all, we write tan x power n as tan x power n minus 2 tan square x. Point number 1. It's very easy to understand. Tan x power n, because adding this amount, that is adding these two powers, you get n. So n minus 2, 2. Why so? Because 0 to pi by 4, tan x power n minus 2 is tan square x, we are writing secant square x minus 1. Because secant square x minus tan square x is 1, therefore tan square x I am replacing by secant square x minus 1. Secant square x minus 1. Now see here, we are reducing this into two integrals, in which in the first integral you get this product tan x power n minus 2 secant square x. In the second integral, tan x power n minus 2 into minus 1. So therefore, we are getting in is equal to 0 to pi by 4 tan x power n minus 2 secant square x, one integral, minus integral 0 to pi by 4 tan x power n minus 2 x dx. Tan x power n minus 2 dx. Now here in is tan x power n. Therefore tan x power n minus 2 is in minus 2. We are having a very simple, that is here my in minus 2. If you have n minus 3, write in minus 3. If you have n minus 4, in minus 4. Like that. We are expressing in terms of in minus 2. Provided you know how to integrate this. It's a very simple integral. For this integral, we are giving substitution y is equal to tan x. Y is equal to tan x. Then automatically dy is equal to secant square x dx. We are having a very good substitution, everything. So therefore, in is equal to 0 to pi by 4. Tan x power n minus 2 is nothing but y power n minus 2. The secant square x dx is replaced by dy minus in minus 2. So only thing is, we are having a very simple integral. Anybody can integrate this. Integrating y power n minus 2, plus 1, we get y power n minus 1. We get y power n minus 1 by n minus 1 with limit 0 to pi by 4. If you convert by, I told you, whenever you give substitution, when x is 0, y is 0. When x is pi by 4, tan pi by 4 is 1. So therefore, by changing the limits, you get 0 to 1. So here 0 to 1 minus in minus 2. So applying upper limit, we get 1 per n minus 1 by n minus 1. Therefore, the reduction formula is in is equal to 1 by n minus 1. In is equal to, I write here, in is equal to 1 by n minus 1 minus in minus 2. This is our reduction formula for tan x power n, 0 to pi by 4. What's the advantage here? Let us take one problem. By writing the reduction formula first. In is equal to 1 by n minus 1 minus in minus 2. Where in stands for 0 to pi by 4, tan x power n. Now usually in competitive examination, such as IIT, they will ask, find the value of I4. According to the reduction formula, I4 is nothing but 1 by n minus 1, 3, 4 minus 2, 2. I4 from the reduction formula which you have derived, by replacing n by 4, you get I4. I4 is 1 by 3, in minus 2, 4 minus 2, 2. To find I4, we require I2. That is the reduction formula, successive reduction. We find I2. Put n is equal to 2. We get 1 by 1 minus I0. Finding I0 is very simple. Once you know I0, I2 is known, I4 is known. So therefore I0 is nothing but 0 to pi by 4 tan x power 0. Because in the reduction formula, in this in, I am replacing n by 0. Tan x power 0 is 1. Integrating 1, you get x. Applying upper limit, you get pi by 4. Therefore, I2 is nothing but 1 minus pi by 4. Once I2 is known, I4 is known. I4 is 1 by 3 minus 1 minus pi by 4. So I2, you get I4. So 1 by 3 minus 1, you get minus 2 by 3. You get minus 2 by 3 plus pi by 4. So this is the value of I4. We can get the value of I5. I5 will be in terms of I3. I3 will be in terms of I1. You find I1 from the fundamental integral and get the value, substitute here. From I1 you get I3, from I3 you get I5. You want I6. I6 is to be in terms of I4. I4 is in terms of I2. I2 is in terms of I0. By successive reduction, you get everything. So we can also write a computer program. Once you give a reduction formula, to the computer, by iteration, we can find the value of I100, I2013, I4000. Any value can be obtained by successive reduction. computer iterates and gives a value for any integral provided n is known. So therefore, this type of reduction formula is very, very useful for all competitive examination. At the same time, this reduction formula can be used in so many places, it has got wonderful applications. You try to solve many problems and enjoy yourself. Okay. Now we are having reduction formula for sin x power n, we are having reduction formula for cos x power n, that is same as this one, and we have seen reduction formula for tan x power n also. Okay, so we will stop with this today. Next class, we are starting a new chapter, namely complex numbers. We are discussing complex numbers with application to computer graphics. That's done in next class. Okay, thank you very much.